So, welcome to lesson 5.2, which is all about population. And this is arguably the heart of theoretical history, because it's the growth of world population that has driven processes of historical change. For example, with the development of technology to feed larger numbers of people, and also the evolution of economic and political institutions to manage societies with large populations. And even today, as world population growth is slowing down, it's still demographic issues to do with population, such as the aging of populations or population movements, mass migration, that are driving the challenges and conflicts of our world today. So population remains a very important factor in historical change. And in this first part of the lesson, we're going to discuss the ideas of Malthus, whom we've come across before, Thomas Malthus, 18th century clergyman who wrote about population, principles of population growth. And in theoretical history, we'll often come across talk of, the Malthusian principle, the Malthusian perspective on population, Malthusian dynamics, Malthusian this and that. So it's important that we understand what the ideas of the Malthusian perspective are, even if it's only to argue against them, as we will may do later. So to think about Malthus, we'll start with the idea of the carrying capacity. So carrying capacity is just the idea that a given place, a given environment can support a certain maximum number of people. So if you're, say, a foraging population, a primitive hunter-gatherer population, you feed yourself from your local surroundings. And you might have, say, 10 people in your band, and you go out and you collect the food to feed your band of 10 people. Now, if you double your population, you've got more people to go out on the food quest, so you can probably collect more food, but maybe not twice as much, because you may have to start going further afield to find food to feed 20 people rather than just 10. And so you'll spend more time walking around and less time actually finding food. So as your population grows, your ability to find food increases, but maybe not as fast as the population itself is increasing. There's an effect of diminishing marginal returns. So if we plot, say, population along here and food up here, then we're going to have something that looks like this. It bends over, it slows down. As population increases, the amount of food available, from what you can find, is increasing more slowly than your population. And it also applies if you're farmers, let's say. If you're a farming village and you double your population, you can probably farm more food with twice the number of people, but maybe not twice as much, because you'll start to have to bring into use the second-rate land and the land that's further away. So again, you'll spend more time walking out to the fields, and there's more chance of losing some of the produce as you bring it in from far away. So the food availability increases at a rate less than the population increase, whereas population itself, the food required to feed the population, that does increase linearly, because each person requires a certain amount of food. So if you double the number of people, you do double the number of food you need. So the food needed increases linearly. And eventually, because this is showing diminishing marginal returns, the food required is going to hit the food available. And at that point, the food, this population here, the food available meat is the same as the food required. And if you go beyond that, then the food required will exceed the food available. And that means there's not going to be enough to go around. And so you can't live like that because people will be starving. So this is the carrying capacity. The maximum population that can be supported. Well, strictly, I suppose this is the carrying capacity. The value of population here, that's the carrying capacity. But this is when you're at the carrying capacity. So Malthus said that because population tends to grow, but it can't grow beyond the carrying capacity, there have to be checks on population growth. So we'll have a look at his ideas about that. Checks on population growth. Checks that stop the population growing beyond the carrying capacity. So Malthus realised that carrying capacity can increase through technological change, technological improvements. I mean, he was living around the 1800s, so he was, living in the time of the Industrial Revolution. He was seeing technological advances improving the ability to support population. So he said that carrying capacity certainly can increase. So if we put here, this is carrying capacity. He said that it is arithmetic in its increase. It increases at a steady rate. There's a certain amount. This is time along here, by the way. Carrying capacity changing over time. It increases by a certain fixed amount each year. Now, why did he say it is increased in an arithmetic way, adding a certain fixed amount? It's not clear that that's necessarily true, but that's what he felt was the carrying capacity can't increase that quickly through technology. It takes a while to invent new things and for them to spread through to start feeding more people. Whereas he said population increases geometrically, was his term. So there's population increasing, as we would say, also exponentially. It increases not by equal amounts each year, but by an equal ratio. The more people you have, the more babies can be born, and so the faster population can grow. So it runs away with itself in this exponential manner, or as he said, geometric versus arithmetic, adding equal amounts to increasing by equal ratios. And so even though through your technology you can improve your carrying capacity, population is going to rise and hit carrying capacity and can't go beyond it. So this is when checks start to have to come into operation. And he said there are two types of checks. There are the positive checks, which operate when you have come up to this Malthusian limit of the carrying capacity, and you've kind of, maybe if you've gone beyond it a bit, then the positive checks will bring your population back down. And they will be things like famine, because you've gone beyond the carrying capacity. You've got more people than can be supported. So people are starving. So famine will cause people to starve, to die, and reduce the population. That's a positive check. Also disease, because when people are malnourished and packed together in large populations, disease can easily spread. So that will also bring the population back down. Or it might be war, because people are living at the margin of existence, There's a scramble for the few resources. People are desperate to get enough to feed themselves. So there will be a lot of conflict as people struggle to secure resources for themselves. Or it may just be a little bit more optimistically just migration. If there's not enough to go round, then population may just move away through migration to somewhere else where there is more resources available. But so these are positive checks, but all of these are kind of disruptive. And he said then the alternative is negative checks, which is where people avoid getting into this situation in the first place. So they limit their families. So negative checks, is basically population control, family planning. So things like late marriage, delaying your marriage to later, so you then will have fewer children, or just abstinence, sexual abstinence, not reproducing, or at least choosing to have small families. And so his argument was that if we just relied on the positive checks, then people will always be living in this world of famine and disease and war and desperate populations moving around, because they'll always be up here, getting up to the carrying capacity, where there's only just enough for everybody. And it's much better if we could get people to use these negative checks, teach people to have smaller families, to get married later, and then we could possibly live somewhere down here with a population below the carrying capacity, and then there would be plenty to go around for people. They'd be able to live better than just at the margin of subsistence. They'd be able to have a bit extra. And in fact, it seems that people are able to apply negative checks and limit their families. They're not just inclined to reproduce blindly to the absolute maximum that they can. And this is seen in something known as the demographic transition. So the demographic transition occurs in societies where there's a decrease in the death rate that is eventually matched by a decrease in the birth rate. So if we plot here time along there, we're in a society where let's use different colour, death rate here is high. But at some point there's some kind of new factor, an innovation, something like the invention of penicillin or improvements in public health, realizing that letting sewage into your water supply causes cholera, so preventing that happening. So something like that causes a fall in the death rate. And the death rate then moves to a lower level. So this is death rate. Well, what happens in such a society is that at first the birth rate is high, because there's people dying off, so people also being born at a certain rate to counteract that. And so after the death rate falls, the birth rate tends to stay steady for a while. But then people start to notice that the death rate has fallen, and so they don't need to have so many children just to have a few of them survive to adulthood, because in traditional societies as well, children are kind of your old age life insurance policy. But when people realise they don't need to have that many children just to make sure they've got a few heirs, then the birth rate starts to fall. And particularly remember that, particularly in traditional societies, mortality is particularly infant mortality. It's people in their, large proportions of people in their first few years of life are dying. So this death rate is particularly applying to children. And so when there's a fall in the death rate, it's particularly among children as well that you see that fall take place. And so more and more children will be surviving to adulthood. And so then this blue line representing the birth rate then also comes down. So death rate, birth rate. The death rate falls, later the birth rate falls, comes back down to match the death rate. You realise you don't need to have so many children just to have some survive. And then if we plot what population growth would look like with this pattern, well, here the birth rate is just slightly above the death rate, so population growth is low. There's just maybe a little, a few more people being born than are dying. So it says the population is slowly growing. But then here, during this point where the birth rate is high, where the death rate is low, now the birth rate is much higher than the death rate. So there will be a large population growth rate. Lots of people being born, not many dying off. But then you get back to here, and the birth rate falls back to the death rate. So the birth rate and death rate pretty much match, and population remains more stable or just growing slowly. So population growth looks like that. There's a pulse, a surge of population growth. And then lastly, if we just plot the actual population, how that will change. Well, at first it was growing slowly, and then here is a sudden surge in population, so a fast growth rate, and then it plateaus again and stops growing, or at least just growing at a steady rate. And so this is the demographic transition, a change from high birth rate, high death rate to low birth rate, low death rate. But there's a sudden surge in population growth leading to a great jump up in population during that demographic transition. Now Malthus was living somewhere around here when around the time of the Industrial Revolution, public health improvements in standards of living were bringing the death rate down, and but the birth rate was still high. So this is Malthus here, and so he is very concerned about this tendency for people to have far too many children and population to be growing far too fast. And what happened in the developed countries in Europe, in the Western world, was it went through this demographic transition and went back to more stable populations or slow growing populations. But this set off a wave of demographic transition around the world. And so in the 60s and 70s, people were again concerned about population growth of the world being too high and straining the Earth's resources, because they were also living in this kind of moment, not particularly in England as Malthus was, but in the world as a whole. They saw this very high birth rate and very high population growth rate. But in fact, that wave of demographic transition has spread out through the world and now affected most of the world, and the population of the world as a whole is now stabilizing because the demographic transition has occurred all around the world. Okay, so the demographic transition tells us that people can limit their families, as when they see this new situation with a low death rate, they don't keep their foot on the pedal and just keep accelerating in population. They realize that they can ease back. So people are able to effect those negative checks. But we're going to step back a little bit and talk about the idea of the Malthusian trap. So we've seen this idea that there's a carrying capacity, and even though it's increasing, population is always going to be able, because it can grow exponentially, it's always going to be able to get up to the carrying capacity. That suggested to Malthus in his day that population will always be at this maximum limit, at its carrying capacity. And the Malthusian trap is the idea that if you improve your technology so you can feed more people, you don't actually get any benefit from that, because you can feed more people, but then the population increases to take up the slack, and you end up back where you started with your population at the maximum that can be supported. So there's just enough to go round for everybody. So the Malthusian trap is saying that throughout history, people will always be poor and living in misery, because they'll always be up at that level. And even if they find ways to improve their food supply, they just end up back where they started. They're just trapped at that Malthusian point where population equals carrying capacity. Well, we've seen in the demographic transition that people don't necessarily behave just like that. They're always increasing up to the maximum possible. They can think about how many children they need and what's supportable. And in fact, anthropologists looking at foraging societies find that they deliberately limit their numbers. They keep them at a certain level, that they don't go beyond. And that level tends to be the level that they can feed during the leanest years. So even when there's been bad weather and not so much food available, there's still going to be enough to go round. So they can think ahead and keep their population suited for not just for the average year, but for the worst years. So they're always going to be okay. And similarly, people studying the age of marriage in early modern England have found that it fluctuates with the economy. So when the economy was doing worse, people married later. So, again, it shows people are sensitive to thinking about how many children they can afford, or whether they can afford to get married and afford to have a family. They are sensitive to these things. So there is some kind of feedback. So people aren't necessarily going right up to the limit. It's perhaps a bit more complex than that. People sort of try to aim for somewhere below the limit, that's acceptable, not up to the minimum possible level. There's some level below that people aim for, but still the Malthusian trap applies, but possibly in a more complex way. But the trap is still there, that even though you improve your technology, you will just keep tracking it, so you'll always have only enough, or what people's mental minimum is, to go round. But in fact, if we look at people's standard of living in England, there are statistics on this, going back to the year 1200 up to today, put 2000 for round numbers, and I say standard of living is measured in terms of real wages, so what wages are really worth. So because of the inflation that's occurred over historical time, over these centuries, a pound today is worth a lot less than it was in Henry VIII's time, or what have you. But if we think about it in terms of its purchasing power, what it could buy you, what you could actually get for your money, that gives us real wages. what is found is that real wages fluctuated up and down with ups and downs of the economy, but remained at a pretty steady level until around 1800. And at that point, they suddenly started to increase. So this seems to illustrate that, yes, there is a Malthusian trap that applied for a lot of history, because there were great technological changes over this time from 1200 to 1800, but real wages didn't increase very much or at all. People's standard of living remained pretty much the same. But from 1800, standards of living increased. People's real wages massively increased relative to what they had been in earlier centuries. So this represents an escape from the Malthusian trap. And of course, 1800, we're talking the Industrial Revolution. So industrialization allowed societies to escape from this Malthusian trap. And then this underlies something we considered in the last lesson, the Great Divergence. So we can plot a chart like this, again showing real wages or standard of living up here, back as far as 10,000 BC. And this is kind of an extrapolation of what we can actually show quantitatively from the statistics that are available in the English economic series. But we can kind of project that back to 10,000 BC and suggest that for most of history since the beginnings of agriculture, standards of living have remained at this steady point, the Malthusian trap that operated for most of history. And then around here, 1800, as we've seen, the developed countries, anyway, the industrializing countries, escaped the Malthusian trap, and standards of living in the developed countries massively increased. But the underdeveloped world remained stuck in the Malthusian trap. And so this has led to the great divergence in standards of living between the developed and the underdeveloped world. As the developed escaped that Malthusian trap, but the underdeveloped remained in the Malthusian trap. So they weren't just sort of somewhere lagging behind, but they were actually in this Malthusian trap, this standard of real wages that has operated throughout history. And then as industrialization has been able to spread, this has been able to, start the underdeveloped world coming out of the Malthusian trap itself, and leading to, as we saw in the last lesson, the Great Convergence. So the developed countries pulled massively ahead, but now the rest of the world is starting to catch up. And this development is particularly influenced by, as Korotayev and co argue in their work on the Great Divergence and Great Convergence, human capital. So education. It's education that stops people then practicing this of always increasing the population numbers to what can be supported, seeing any improvement in technology as it spread to the underdeveloped world, but seeing any improvement in technology as just an excuse to increase the population again. But human capital, education, allows people to, or helps people to start using those negative checks on population growth rather than relying on the positive checks. And education, leads to things like work ethic, industriousness, restraint, particularly sort of planning ahead, thinking about the future. So not necessarily just living for today, consuming what's immediately in front of you, but thinking about the future and what's affordable long term. And Also a very key part of it, female emancipation. People would identify as a key part of human capital, so that women's role in society is not just about having families, and women's worth in society is not just about how many babies they can produce. So that is important to being able to escape from the Malthusian trap. And as this is spreading around the world, it is leading to the convergence as other countries start to escape the Malthusian trap. Okay, now where a society is with respect to this Malthusian trap and the escape from it is closely related to its degree of stability or instability. So that if you're at the Malthusian limit, so your population is up against what can just about be supported. People are poor. They've only just got enough, so they've got little to lose. And people who have little to lose are very willing to join revolutionary movements that are sat on, overthrowing the existing order, because they're not getting anything out of the existing order anyway. So this can create revolutionary sentiments, attitudes in the population. And when you've got a lot of people who are pretty revolutionary, then that will lead to political instability, unrest and instability. And certainly in sub-Saharan Africa, it's been shown that the countries with where the population has the lowest calorie intake, so where people are closest to the starvation level, those are the countries that have the most civil war and the most political instability.
Of course, there's a bit of chicken and egg here, and civil war may itself cause economic crisis and famine.
And it's also been argued that the Russian Revolution occurred after a period of rapid population growth in Russia. So rapid population growth that had brought the Russian population up to the Malthusian limit. And this population explosion, then it's been suggested, is more relevant to why the Russian Revolution occurred than Lenin's political theories. That's meant to be a greater than sign. So, the population explosion was more important than things like Lenin's political activity. It was the population explosion, the being at the Malthusian limit, that led to the Russian Revolution. And today, if we're looking at societies around the world, their closeness to the Malthusian limit is similarly an index of their propensity for things like the Russian Revolution, for civil war and political instability. So if you see in a country strong population growth but weak economic growth, then that is a strong index of political instability. It leads to an expectation of revolutionary movements, civil wars and coups and all the rest of it. Now, as we were just saying then, the developed countries escaped from the Malthusian trap, and less developed countries are also escaping from the Malthusian trap over time and catching up. But Andrei Korotayev and his colleagues have talked about what they call a trap at the escape from the trap. So if we have a particular society, real wages over time, that's down here in the Malthusian trap, but it's now industrializing to the point that and it acquiring technologies to the point that it can start to escape from the trap, and it's about to go onto this branch and see improvements in the quality of life, standard of living, real wages. But it's at the moment it's just here. It's about to escape from the trap. This is where they suggest there is a trap that can prevent the society actually getting out and escaping the trap, which has a couple of key parts to it. Firstly, there is the youth bulge, the sudden increase in population due to the demographic transition, because these technologies have brought down the death rate, but the birth rate has yet to respond. So, you're having a lot of people being born. Oops. You're having a lot of people being born, and infant mortality is drastically decreased. So you've got a lot more young people in your population, and they're then surviving to adulthood. So when they're in their late teens, early 20s, you've got this sudden increase in the number of young people, and they tend to be underemployed because the society hasn't got roles for them all. There aren't the jobs and things available. They haven't been created yet. So you've got a large number of young people coming of age and nothing for them to do. So you've got youth unemployment. And at the same time, another key feature of the societies that are here is recent rapid urbanization. Because one of the things that drives this is the ability to feed more people, mechanization of the farms. And so there's less need for people to be out in the country on the fields growing food. They can come in to support industrialization in the factories, and those factories are in the cities. They're not out in the fields. And so you're bringing people into these urban centers. And so you've got a lot of footloose young people with nothing really for them to do, and they're all brought together into these urban environments, packed together in large numbers. Well, they are easily recruited into revolutionary kinds of movements, because being unemployed, they haven't got much to lose, and there's lots of them around. So anyone wanting to foment instability can recruit these to their cause. And so this then can lead to civil war, political unrest, and destructive tendencies that prevent the society actually improving its quality of life. And lead with civil war, for example, it prevents industrialization taking place peacefully. And so that trap, at the escape from the trap, prevents a society going on to this branch up here. And it would just fall back into the Malthusian trap. But what can then happen is that societies learn over time, so that it can then, resolve eventually, get back into more peaceful condition, still in this Malthusian trap stage, but then it tries again to get back onto this other branch and escape from the trap. And this time around, there's been some institutional learning, societal learning, that allows it maybe this time to escape these problems of the youth bulge and the urbanization, and this time to escape from the trap. Or it may be a second time, it falls back, but then the third time it can escape from the trap. So there may be several attempts we can see in the history of development around the world of societies to escape from the trap. And they succeed at last, rather than, it's not something that necessarily happens automatically because of the trap at the escape from the trap. Okay, now let's talk a little bit about population cycles. So with animal populations, they're also subject to the same kind of Malthusian trap, that there's a certain carrying capacity for a particular animal population, and it tends to reproduce up to that carrying capacity, and so be at the level of the carrying capacity. But we also see, though, in animals, population crashes. So the population kind of can increase up to the maximum, and then there's a kind of food crunch. And that food crunch is followed by a population crash, maybe because it increased up to this level, but then there were some lean years, and so the population became too high. And so, if there's not enough to go around, everybody is starving, so the whole population can die off pretty much, and the population crashes, and then it recovers again. So in animal populations, you can see these real swings up and down by large amounts. But in human populations, you don't see quite the same. I mean, it can happen. There can be massive demographic crashes, but they're less common. And what tends to happen more is there's a stagnation for a while, and then it picks up again. And this is because it's been argued humans, are intelligent, and they're able to reason about things and adapt. And the sort of thing that humans do is, store up food for the bad years. So they can be more resilient than animal populations. So what you tend to find with human population growth over time is it might be going up like this, and then there's some kind of crisis here, a bad year, the rains didn't come, not enough food. Population doesn't crash down, but it grows a bit more slowly as a result. But eventually it will come back, and because of the ability of population to grow, as Malthus said, geometrically, or as we might say, exponentially, it eventually gets back on track to where it would have been if that shock, let's say an environmental shock, climatic shock, a bad year. So it gets back to where it would have been if that had never occurred. And it's been suggested that these shocks, you can see them in the population record, and they have a sort of lifetime of about 70 years. After 70 years, the effect has worn off, and it's back to where it started. The population has been able to recover to, or not where it started, but to where it would have been without the shock. So the population is able to recover from the shock after about 70 years. So a big environmental shock produces a decrease in population growth that lasts for about 70 years relative to the general trend. Now, although humans can kind of absorb these environmental shocks, then we do see cycles, fluctuations in population, but they may be more in the form of fluctuations around a trend rather than, and in an animal population we can see real swings up and down. In human population growth, we may see times of greater and lesser population growth. But so there are cycles, fluctuations, oscillations in population, but they tend to be more around a trend. And with these fluctuations, oscillations in population, we find, if that's population over time, we find that they're correlated with real wages. So that when population is high, real wages are low. And then as the population grows more slowly for a while, real wages increase. And so at the sort of downswings, the real wages are high, standards of living are high. At the upswings, large population, standards of living are low. And that rather suggests then that this is a kind of Malthusian dynamic, because it seems to be that the low real wages at the peak of population causes people to rein back on population, to have fewer children. They feel they can't afford them because there's, seemingly not enough to go around. Wages are low, so that the population falls back, and then because that allows, that means there is more to go around and allows real wages to rise. Then people start to have more children again. They feel more prosperous, and they can afford to have larger families, and then that brings you back up to a peak of population again. So these fluctuations in population seem to be reflecting a Malthusian dynamic, and that then raises a question of how can we model this mathematically? Can we produce some equations that predict this kind of fluctuation based on the ideas of Malthus? Okay, now Sergei Nefedov has written a paper, Modelling Malthusian Dynamics 2014, which provides a review of all people's attempts to model these cycles in population using Malthusian ideas. And that's in the journal History and Mathematics, which you can find on the sociostudies.org website, which I mentioned as a source in Module 1 of this course. And what Nefedov shows is that there have been many approaches. Some use dynamical equations, differential equations, calculus, so continuous modelling of population over time, and others use discrete iterative approaches. They take the population is so much in this year, and the amount of food is so much in this year, and then that affects how the population changes to the next year. So it's basically doing the same thing, but in steps, rather than trying to produce a set of calculus-based differential equations. And also some models use the idea of exogenous random shocks. So bad harvests come along at random intervals. Others try to model it all endogenously. So there's no randomness to it. There's nothing coming in from outside. It's all contained within the equations, the ups and downs. So we'll look at a couple of models to give the feel for the variety. So the first one is two authors, Brander and Taylor, and I'll just write up their equations first. Okay, so in their model they have a food supply S, which is something like game, something that rabbits might be, things that you go out and catch and that reproduce themselves. So this food supply obeys a logistic growth law. So you should recognize that from our mathematics module, that it is going to increase up. Well, it's kind of exponential because it's proportional to itself. R is just a constant rate of growth. But it's also modified by this 1 minus s over k. So as s approaches k, which is the carrying capacity for the food supply, not for the population we're interested in, but the carrying capacity for the rabbits or whatever it is we're eating, as these food supply approaches its own carrying capacity, this will become 1 here, this will become 0, so it will stop growing. So it's just going to there's s over time. It will, if nothing else is happening, increase logistically up to this level k. That's just a standard logistic equation. But it's also got this additional term which represents consumption. The population P is eating the food supply S. And the more people there are, the higher the population, then the more of it they eat. This obviously is a negative contribution to growth because they're eating the thing, so they're decreasing it. So that's causing a negative growth in the food supply by eating it. And it also depends on the food supply itself. S, U is again just a constant multiplier, but it also depends on the food supply S on the basis that, you know, if there are lots of rabbits around, people will be more successful in catching them. So the more the food supply, the more quickly people will be able to harvest it. And then the population grows just exponentially, basically. It's just proportional to population, but it depends on a constant D. And if you ignored that, this would just be the population growth rate. Well, this whole thing is a population growth rate. This would just be its kind of natural growth rate. But it can also grow at the rate depending on how much it's able to eat. And so the population growth rate increases. Nu here, the Greek letter nu, is a constant multiplier on S. And so the more the food supply, the faster the population can grow, the greater the growth rate. And with these two equations, they can generate oscillations. But those oscillations tend to die out. They're transient. After a while, it just settles on a particular value of S and P. The food supply and the population reach a kind of equilibrium. And I meant to say at the beginning, in fact, that one of the key challenges for these models of Malthusian dynamics is reproducing oscillations in population, because what you sort of logically tend to find is that as a population reaches the Malthusian limit, it might fall away from that, but as soon as it falls away, then people are better off, and then they just grow back to the limit. So they kind of immediately grow back to the limit. There's no reason why population should continue decreasing. Once the population has decreased a little bit below the Malthusian limit, then it's suddenly freed from those pressures, and so it can grow back. It won't keep falling. So trying to write models that do cause an oscillation rather than just constantly bumping up against the limit is a challenge. And so this model, it manages to show why there's it manages to produce an oscillation, but it's only transient. It dies out after a while. So that's one problem. And the second problem is it's not really Malthusian anyway, because in this one, the food supply itself is fluctuating. It's actually kind of a partial Lotka-Volterra equation, set of equations. This is, again, we covered that in the mathematics module. It's because it's partially Lotka-Volterra that it gets the swings that we see in Lotka-Volterra, but it's not fully Lotka-Volterra, and that's why they die out. And but in the Malthusian case anyway, the food supply doesn't fluctuate. The whole point of Malthus is there's a kind of constant carrying capacity, and you bump up against it. But Malthus is not saying the carrying capacity is decreasing. If anything, it's steadily increasing. But you're always, matching its growth, and so you're always up to the limit. And this is why you're always as poor as you possibly can be before you actually start to die off. So this logistic aspect to its growth, and the fact that this food supply is fluctuating up and down is not really a Malthusian dynamic. So that's one example there of modelling Malthusian dynamics. And another one, and this has been implemented in various forms by numerous people, even in Sid Meier's Civilization series, for example. But you have a set of farmers, let's say. Those are your population of farmers, and they grow a certain amount of food each year. So this would be an example of the kind of iterative model. it's stepwise, so you do it year by year. So you've got the farmers, and each year you have a certain harvest. Let's perhaps put that in, harvest. And that may fluctuate through random external shocks that sometimes you have good years, sometimes you have bad years. With their harvest, they can consume it, consumption, eat to survive, and they can also divert some into storage, saving it for a rainy day or saving it for a bad year. And so each year the farmers, because of their population, they have a certain amount they need to consume, because each person needs a certain minimum. At the harvest they will consume a certain amount, and anything left over goes into the store. And as they consume, then they're able to increase their population. And when you have a bad year, bad harvest, then they can cut it. They may have their population maybe too large to cover their consumption needs. That's when they can draw on their storage, and so smooth out the bad harvests. And this is capturing the idea we saw earlier, that humans don't just crash in population, but they can absorb some of the shocks through their forward planning and things like storing food. But nevertheless, you can then have, just through pure bad luck, a series of bad years. And if you haven't had a long run of bad years for a while, you've built up a big storage, and so you think, oh, this is great, we can expand our population and have big families. And so your population starts to grow, and then by random chance a series of bad harvests comes along, and your population is growing very high, and you start to draw on your storage, and that's fine for the first 2 or 3 years, but then you're still having more bad harvests and you run out, and then you can't cover your consumption needs, and then your population crashes, and it can crash in a big way. And then it takes a while to start to grow back up through successive harvests, because you start to need to build back up your storage, and then once you've got your storage, then you can start to put extra into consumption to have larger families. So this can produce these cycles in population, but it does rely on external shocks. It's not built in. It's your model, you're throwing a die at each step to take a random value for the harvest. But with the exogenous shocks, then you get cycles. But it's not really satisfactory to have relying on something random. You would like to be able to model this all endogenously through causes that are closed within the model. And that leads to the structural demographic theory, which we will briefly consider. Okay, so as we saw in the discussion of models just now, then if this is a chart of population against time, we might have a carrying capacity. That's what this black line represents, the carrying capacity that's steadily increasing. And we might expect the population just to bump up against this, because as we said, if the population gets too close to the carrying capacity, so people are very poor and the population falls, then immediately they'll be fine, and so they won't want to, the population will have no reason to keep decreasing, so it will just keep coming back to this level slightly below the carrying capacity, and there won't be any oscillations. But what we actually see is something like this. So there's some overall trend, which we can assume is a trend in carrying capacity, and the population doesn't just track the carrying capacity, it doesn't just bump along underneath it, it swings up and down. There are these long period, maybe decades to centuries, swings in population. And it's explaining this that was the problem for these models, trying to explain why there are these swings rather than just tracking the carrying capacity. And we saw a couple of models. One way to do it is to use the kind of Lotka-Volterra approach, but as we said, that kind of only works for a few swings. Another is to introduce random shocks that cause the population to fall back and from which it has to recover. But neither of those are really satisfactory. The structural demographic theory tries to explain it, or succeeds in explaining it another way, which is by saying that it's not just a demographic issue, that it's not, when population increases, it's not just an increase in population numbers, but there's also a change in the structure of the population. And these changes in structure take a while to develop and then to undo themselves once population falls. So oscillations occur in systems when there is a lag. So a pendulum swings because as it's moving in this direction, it's being pulled back in the opposite direction, but it has some momentum. And so it takes a while for the force of gravity to overcome its momentum, to slow it down and bring it to a halt. And then it will start to swing back. But once it gets back to the middle, it's now got momentum in this direction. So it goes past the middle and gravity is trying to pull it back. But because it's got some momentum, it will keep going up and then eventually come to a halt and then start swinging back, and so on. Well, that's what we need in to explain these oscillations in population. We need some kind of lag, something that takes a while to undo, like the momentum of the pendulum takes a while to bring to zero so you can start moving back. And it's these changes in structure that provide that kind of lag to the response of the population to the signal it's receiving from, its level of poverty, where how close it is to the Malthusian limit. And we'll talk in detail about the structural demographic theory and how it does that in module 8 of this course on social cycles. That's something, for the future. But just to give a quick feel for the sort of thing that's involved, is that when the population increases in structural demographic theory, it doesn't just mean that people have or people have bigger families, but compared to in previous times when people had smaller families, they only had maybe one son per family. Now, when they have bigger families, it means they've got a second son, possibly. And a second son is rather different from a first son, because a first son can step into his father's role. But a second son is a bit of a spare part. He hasn't got a role to step into. So he has to find some other way of justifying his existence, do something else with his life. So this creates stresses in society, finding roles for second sons. And that's a kind of change in structure. So it's not just a change in the size of the population, but there's also a change in the structure. And because those second sons are going to be around for their lifetime, potentially, then that creates a lag for that to work through the system as you move back towards only having one child per family or only one son per family. So that is where these cycles come from, the lag as the structure builds up and then unwinds again. And lastly, we're going to consider the issue of global carrying capacity. So as we saw with Malthus, living at the time of a demographic transition in England, he was very worried that there were too many people for the world to support. But since Malthus's day, the population of the world has increased by a factor of 8. So it's doubled and doubled and doubled again. And yet people live better today. Life expectancies have increased. So although Malthus thought, the world was coming up against what it could support, and technology just wasn't going to be able to increase fast enough to keep this exponentially growing population from ending in terrible poverty. In fact, the population has doubled and doubled and doubled, and also people are living better. They've escaped from the Malthusian trap. So Malthus's ideas about how many people the world could support seem to have been wrong. The world could obviously support a lot more people than he realised. And that raises a question of, well, how many people can the world support then? What is the total number of people that could potentially live on the Earth, given the resources that are available here? And the United Nations Environment Project, UNEP, invited 65 expert teams to provide estimates of what the carrying capacity of the world is. And all these experts decided it's about 8 billion. Let's put that 8 times 10 to the 9 people. According to the UNEP experts, that's a global carrying capacity, 8 billion people, which happens to be pretty much what it is now. But that raises a question, well, okay, so they're finding that the global carrying capacity is pretty much what we've got. But is that then just a lack of imagination, a bit like Malthus? Because Malthus thought in his day that the carrying capacity was round about what it actually was. And he didn't think about, all the technological improvements, the internal combustion engine, etc., that would lead to a much greater increase in, or much higher level of carrying capacity. So is this the same kind of failure of imagination? And also, is it just political? Is it driven just by saying, well, there are too many people, therefore we need to implement all these programs to make the world more sustainable? So it does seem a bit strange that what they found the estimate to be was actually what it is now. So what other estimates are there? Well, Julian Simon, economist, who was a great optimist and set himself against the vast majority of scientific world who were saying that there are too many people. He said no, not at all. There's the ultimate resource. So if you're worried about the world running out of resources, don't, because there is the ultimate resource which will never run out, and that is human ingenuity. He said if you actually look through history, the price of all resources has come down. Things have got cheaper and cheaper, and that's because of human ingenuity and discovering things that we didn't even know were resources, like oil. The Romans didn't know that was a resource, but to us it's an important resource. And there were other future things that we may be able to draw on through human ingenuity to keep our population alive and keep us growing and improving technologically. So I can't tell you what they are, because that's in the nature of the whole thing. But we do know, we've seen thousands and thousands of years of human ingenuity always improving our conditions of life through discovering new things, and that will just go on forever. So if we took that, then it would imply there's really no limit to how many people the world can support, because human ingenuity, if we're a supreme optimist like Simon, will always overcome whatever challenges and difficulties we might face. And he put his money where his mouth was, because he challenged Paul Ehrlich, who was one of the people back in the 60s who thought, didn't even think 8 billion was possible. In the 60s, Paul Ehrlich, wrote the Population Bomb book, suggesting that the world was all going to collapse because there were too many people. And Simon said, no, human ingenuity, ultimate resource. And he said, I'll bet you that certain resources that you're predicting will become unaffordable will actually fall in price. I think one of them was copper. So he bet Ehrlich that, he said it would fall, Ehrlich said it would rise, the price of copper. And he won the bet. And the reason, say, something like copper fell in price is because copper was a very important need for telephone wires and electrical systems, but for telephones. But then the mobile phone came along. So any projections made on how many more telephones people would need in the future showed that the demand for copper will be tremendous, and there's only so much copper to go round, so we'll run out of copper and the price will shoot through the roof. Well, it didn't happen because mobile phones came along, and so actually those projections for how much copper would be needed to support the telecommunications needs of the future were wrong. They were based on a failure of imagination about how human ingenuity would change the whole way telephony works. So Simon actually did win that bet, but nevertheless, the people who take the opposite view that we're close to the limits of what the Earth can support say, well, yeah, you won it, but only by fluke. And actually, maybe the next year the price went up again or something. So so they didn't necessarily accept that Simon was correct. It was seen as like a lucky. He got lucky. Now, Cesare Marchetti has produced a paper where he goes through a whole series of calculations to work out the global carrying capacity, and he finds that it is 1 trillion, the global carrying capacity, 10 to the 12 people. And this amounts to 5,000 people per square mile. So you can see, compared to this, this is, almost 100 times what these experts are saying, Marchetti's saying, or in fact, slightly more than 100 times. If that were 10 times 10 to the 9, this is 1,000 times 10 to the 9, 10 to 12, so it's over 100 times what they were saying. And it amounts to 5,000 people per square mile, and that's including the oceans. That is, assuming people have spread into the ocean. So you count the surface area of the oceans in your calculation in terms of the number of square miles. Then you've got 5,000 people over the whole Earth, including the land and the oceans. The oceans then are a vast untapped resource for humans at the moment. But assuming we can move into the oceans through human ingenuity and start to colonize them, spread out all over the surface of the Earth, then there'll be 5,000 people per square mile, which you can compare with 13,000 people per square mile in London. So it's actually less than half of the population density of London. Let's put that in London. And 13,000 per square mile is by no means the densest city in the world anyway, and is obviously reasonably tolerable because a lot of people live in London. And yes, there are areas where people are packed into high rises, but there's also a lot of parks and open space. So at 5,000 per square mile, it is livable. So that's why it gets 10 to the 12. Another calculation that was done in the 1960s, someone called Fremlin, J.H. Fremlin. He said that by AD 3000, he projected forward the population growth rate that applied in the 1960s, and at that time that was just before the population started to turn over. So in the 1960s it had been growing exponentially, or at an accelerating rate anyway, for a long time, and it was continuing to accelerate. But by the early 70s it was starting to turn over, but in the early 60s it was still going up. And he said if you project that forward, by AD 3000 there would be 60 times 10 to the 15 people. So that is 60,000 trillion. So 60,000 times what Marchetti estimated, AD 3000. And he suggested this, for this to be possible, this would mean that people were crammed in all around the world, shoulder to shoulder. You know, you'd only have the footprint of your body to stand within. And he said that this could be achieved then if people just didn't move, they just stayed in one place and were entertained by TV all day long, then this is the world that, you know, would be possible. So I don't think that was a serious attempt to describe what the global carrying capacity is, but it's just a kind of thought experiment to see, you know, what it would imply if these population growth rates continued. But you know, Marchetti would certainly say that, okay, we may not go this far, but this 8 billion is not really based on anything very substantial, and it can be a lot larger than that without really causing great problems for humanity. You know, we've still got a lot of space to move into, especially if you consider the oceans and the resources of the oceans. Well, what may though suggest that the UNEP could be closer to the truth is the very fact that the population is now slowing down, and population growth rates everywhere have, you know, approaching zero, and the population of the world is kind of stabilizing maybe around at 8 billion or not much more. And you know, that would imply that people are feeling that Malthusian limit. They're feeling that this is a carrying capacity of the earth, and so they're putting the brakes on population. They now feel they can't afford to have too many more children. So it may be a kind of combination of these, that on Earth maybe the population will stabilize around this sort of level, but through human ingenuity we might move beyond the Earth into space and onto other planets that will provide the possibility for the population, the human population, to continue increasing. So it might be that global carrying capacity is somewhere around this. Personally, I kind of doubt it, because I would think that even if people move onto other planets, then the effort, the industry on other planets will be able to support more people back on Earth. And Earth might become like, you know, London, a very highly populous part of the solar system, but in other parts of the solar system they'll be emptier. You know, they're on the moons of Jupiter or something, there'll be lower population densities. So anyway, who knows, but human ingenuity is the wild card here, and trying to put a figure on global carrying capacity or the maximum size of the human population is, you know, a very difficult, if not impossible task, because it involves unknowns. And so, you know, there may be some arguments for this, but there should also be some skepticism about it.